The purpose of this module is to provide an overview and component location of the 767 hydraulic system by describing system operation and identifying the major components within the system and showing their respective locations. The main function of the 767 hydraulic system is to provide full power control for flight controls, landing gear, brakes, nose wheel steering, and thrust reversers. The latest technologies in design have been employed to provide high reliability and low maintenance. For example, 3 independent hydraulic systems provide power for normal operation. Where possible, serviceable components for each system are grouped in one location for ease of maintainability. Common components are used wherever possible, allowing interchangeability. Tubing runs are routed so that no one major malfunction incapacitates more than one system. Erosion is reduced through the use of BMS 3-11 Type 4 fluid. The 3 independent hydraulic systems are the left, the center, and the right. They are color-coded, red, blue, and green, for system identification. Each system provides 3,000 psi pressure. The primary flight controls, consisting of the autopilot and central control actuators, spoilers, ailerons, elevators, and rudder, receive power from all 3 systems. This provides triple redundancy for the main flight controls. Other controls, such as the elevator fuel system, stabilizer trim, and yaw damper, make up the secondary flight controls. The left and center systems provide for their operation. The right system provides normal braking, and the center system provides an alternate and reserve brake system. Single power services are the engine thrust reversers on both the left and right, and the leading edge slats, trailing edge flaps, steering, and landing gear, all in the center system. The controls and indicators for the hydraulic system are located in the flight deck. They are primarily located on the P5 overhead panel. The controls for the left, center, and right systems are contained on this panel. Each system is arranged vertically. Starting at the top of the panel, low pressure system lights, low hydraulic quantity lights, 4 primary pump switches, primary pump low pressure lights, primary pump overheat lights, demand pump low pressure lights, demand pump overheat lights, and demand pump switches. Located between the P1 and P3 panels, the engine indication and crew alerting system, commonly known as ICAS. The upper ICAS display will indicate the cause for any hydraulic warning light that appears. The lower ICAS display will indicate the fluid quantity of the reservoir on the status page. When requested, hydraulic quantity, pressure, and temperature are recorded for the ICAS maintenance page. The P11 panel is located behind the P5 overhead panel. Hydraulic circuit breakers are located on the P11 panel. Located on the P6 panel, the main power circuit breakers. The left and right systems are similar and are located around each corresponding engine. The primary pressure source for each system is an engine-driven pump, or EDP. Even at idle speed, the flow from this pump exceeds the highest demand expected for the operation of the flight controls on the left or right system. The second pump in this system is called an alternating current motor pump, or ACMP. It is a secondary or demand pump. In flight, it is a backup source for the EDP. On the ground, it is used to pressurize the system without running the engines. Let's look at a simplified flow diagram of the left hydraulic system. The EDP functions as the primary pump. Hydraulic fluid is supplied to the EDP from a pressurized reservoir. Case drain flow cools and lubricates the pump. It passes through a heat exchanger before returning to the reservoir. The flow from the EDP provides pressure for the primary flight controls, the secondary flight controls, and the left thrust reverser. The ACMP provides a secondary source of pressure for the system. Fluid from the reservoir flows to the ACMP. Case drain flow passes through the same heat exchanger before returning to the reservoir. The ACMP provides pressure to the same subsystems as the EDP. In the reservoir, the EDP draws fluid from a standpipe. In the event of an EDP failure causing loss of hydraulic fluid, there is still some fluid left in the reservoir below the standpipe. Fluid is drawn from the bottom of the reservoir to supply the ACMP. The right hydraulic system operates in the very same manner. The only difference is in the user subsystems. The right system provides pressure for the primary flight controls, the brakes, and the right thrust reverser. Hydraulic components associated with the left and right systems are located within the engine area and hydraulic bay area of each engine strut. Except for the reservoirs, the components are identical. They are located on the same side of the engine in a similar manner for each system. They are not mirrored. For convenience, only the left system components will be shown. The majority of the left system components are located in the left hydraulic bay of the engine strut. Access to the components is provided by opening the bay access door. The left system reservoir, the quantity transmitter. This provides a signal to the quantity light on the P5 panel and a quantity indication on the status page of ICAS. The temperature transmitter. This provides a signal to the temperature indication on the electric hydraulic maintenance page on ICAS. Hydraulic fluid passes through a supply line to a supply shutoff valve. This shuts off the supply of hydraulic fluid to the EDP in the event of an engine fire. This valve is controlled by a fire shutoff switch located on the center aisle stand in the flight deck. The line from the isolation shutoff valve goes forward and down to the engine area. Access to this area is provided by opening the engine cowling. Located on the right side of the engine, an engine-driven pump or EDP. Located on the EDP, a depressurization solenoid valve. It is controlled by the pump switch on the P5 overhead panel. The EDP sends pressurized and case drain fluid to the EDP filter module located in the hydraulic bay compartment. This filter module contains pressure and case drain filters, a pump low pressure and control pressure switches, and a case drain over temperature switch. The low pressure and over temperature switches send signals to the indicator lights on the P5 overhead panel. Hydraulic fluid from the reservoir also flows to an alternating current motor pump or ACMP. The ACMP is controlled by a demand pump switch on the P5 overhead panel. An overheat switch on the pump sends a signal to the overheat light on the panel. The next components are accessed from the inboard side of the left hydraulic bay. The ACMP filter module, located on the module, a low pressure switch. This sends a signal to the low pressure light on the P5 panel. Case drain fluid from the ACMP enters the same filter module and passes through the case drain filter. System fluid returns to the reservoir through the return filter module. There are two ground cart connections, pressure and return. Case drain fluid returns to the reservoir through a heat exchanger located in the fuel cell of the left wing. Access is provided through a panel on the wing. Both the center system and right system heat exchangers are located in the right inboard wing in a similar manner. Located after the heat exchanger, the left system pressure transducer. Access to the area is provided by removing a panel on the wing. Left system pressure is sensed by this pressure transducer located on the inboard aileron support rib. When requested, pressure is recorded on the ICAS maintenance page. A wing control isolation valve is also located in this area. A second wing control isolation valve is located on the left wheel well aft bulkhead. The tail control isolation valves are located in the aft end of the airplane, directly behind the pressurized bulkhead. Access is provided through the access door in the stabilizer jack screw compartment. Two isolation valves are mounted on the left sidewall. A third isolation valve is mounted on the right sidewall, directly across from the others. The wing and tail control isolation valves are controlled from the P61 panel on the right side of the flight deck. The third hydraulic system on the airplane is the center system. Two ACMPs provide the primary pressure source for this system. These pumps have the same part number as the demand pumps on the left and right systems and are completely interchangeable. The flow from the two ACMPs will provide for most demands of the center system. The slats, flaps, and landing gear, however, are high-flow, short-time services requiring a high rate of flow. Therefore, an air-driven pump, or ADP, is provided as a secondary source to accommodate these needs. On demand, this high-volume pump will provide the increased flow required for these systems. The last pump used in the center system is the ram air turbine, or RAT. This pump is used as an emergency source for supplying pressure to the primary flight controls. Let's look at a flow diagram of the center hydraulic system. Two ACMPs provide the primary source of power. Hydraulic fluid is supplied to these pumps from a pressurized reservoir. Each pump uses case drain flow for cooling and lubricating and passes it through a heat exchanger before returning it to the reservoir. Both ACMPs provide pressure for the primary flight controls, the secondary controls, landing gear, steering, and the brakes. The ADP is the secondary demand source of pressure for this system. Hydraulic fluid is supplied to the ADP from the same reservoir. Again, case drain flow returns to the reservoir through the heat exchanger. The flow from the ADP supplies the same user subsystems as the ACMPs. During high flow demand, these three pumps operate together. The RAT provides an emergency power source. Fluid from the same pressurized reservoir supplies the RAT. The fluid is returned directly to the reservoir without passing through the heat exchanger. When the RAT is deployed, the flow is blocked by a check valve to all subsystems except the primary flight controls. This provides for the operation of the flight controls during an emergency. A standpipe is located in the reservoir. It normally supplies all the center system pumps. Two isolation valves, when activated, will isolate this pump from the rest of the system. Reserve fluid from the bottom of the tank supplies the number 1 ACMP when isolated. Hydraulic pressure is then available to the reserve brakes and steering. The components for the center system are primarily located in the right main wheel well area. Access to the components is through the right wheel well door. The center system fluid is supplied by a center reservoir. Quantity transmitter, temperature transmitter. Hydraulic quantity is available on the ICAS status page. Hydraulic fluid temperature is available on the ICAS maintenance page. Reservoir pressurization module. Depressurizing valve. Pressure supply shutoff valve. Located on the keel beam, 2 ACMPs. A case drain overheat switch on the pumps provides a signal to the overheat lights on the P5 panel. There are 2 number 1 ACMP isolation valves. They are controlled by the reserve brake and steering switch located on the captain's P1 panel. These valves are also controlled automatically in the air by low center hydraulic system quantity. The system is reset by a switch on the P61 panel. There are 2 ACMP filter modules. The ADP, or reserve pump for the center system, is located in the left-hand side of the airplane. Access is provided through a snap-fastened and hinged panel door. The air-driven pump, or ADP. The ADP is controlled by a pump switch on the P5 panel. Pressurized hydraulic fluid and case drain fluid go to the ADP filter module located in the aft end of the left-hand wheel well. In the right main wheel well, pressurized fluid from the center system is sensed by a pressure transmitter located above the pressure isolation valve. After passing through a heat exchanger in the right wing, fluid from the center system passes through a return filter module before returning to the reservoir. Ground connections for the center system are located on the bottom of the keel beam between the 2 wheel wells. Access is provided through an access door. Pressure connection, return connection. Located aft of the right main wheel well, just below the right wing body fairing, the ram air turbine, or RAT. Hydraulic fluid is supplied by the same center system reservoir. A manual deploy switch, located on the pilot's overhead P5 panel, extends the RAT. The switch is guarded to prevent accidental deployment. In the unlikely event of a dual engine failure, the ram air turbine will automatically extend from the airplane into the airstream to provide an emergency source for supplying pressure to the primary flight controls. The ram air turbine pump. Located in the right wheel well, the RAT control and checkout module. Located on the module, a back drive handle, and a tachometer module. A guarded switch, located above the tachometer module, provides for rat retraction. Before the rat can be retracted, indicator marks on the propeller hub and swing arm must be accurately aligned. Let's briefly summarize the hydraulic system by reviewing the pumps. 4 different types of pumps are used in the 767 hydraulic system. The first type is the engine-driven pump, or EDP. One EDP is mounted on the end of each engine gearbox. Each pump provides a high volume rate of flow and serves as the primary pressure source for the left and right systems. The next type is the alternating current motor pump, or ACMP. A total of 4 ACMPs are used. One pump is used for the left and one for the right system. Each provides a secondary or demand source. Both of these pumps are located in the engine strut fairing compartment on each engine. The other 2 ACMPs are located on the keel beam of the right main gear wheel well. They provide for ordinary flight operations and serve as the primary source of power for the center system. The third type is the air-driven pump, or ADP. It is located in the left rear fuselage wing fairing. This pump serves as a secondary, high-volume demand pump for the center system. The last type of pump in the hydraulic system is the ram air turbine pump, or RAT. It is located in the right wing body fairing after the right main gear wheel well. This pump serves as an emergency source of power for the primary flight controls. In the event of a dual engine failure, the ram air turbine with pump extend into the airstream to supply pressure to the primary flight controls. This completes this module on the 767 hydraulic system. You have seen the location and function of each of the major components in this system and have been given a description of the system operation.